Good morning, GOBC Chem 114. We're into chapter 14. We're looking at organic chemistry and we're tying that into biological chemistry because that's really where these two worlds come together. Carboxylic acids and esters, amines and amides, all very important in biological molecules. Carboxylic acids form esters, as we've learned. We also will learn that amines and carboxylic acids will react to form amides, and that we'll get what we call peptide bonds. And so nature has amines everywhere. We have this really cool molecule responsible for this blue color that can be extracted from this flower here. And indigo is a molecule that has kind of like a mirror-like look to it, but quite interesting. We have this fused ring, as you see me pointing to these two rings that are fused together. We're going to see that theme in nucleotides. So when we talk about DNA and RNA nucleotides, we're going to see that there as well. Um, so this is very important. Nucleotides have nitrogen in them, and indigo, of course, is not a nucleotide, is actually a dye molecule. It can be used on clothes and fabrics and such. Moving on, we can look at derivatives of ammonia as a way to first kind of define what an amine is. We start with ammonia, and everyone kind of knows that ammonia is NH3 by now. It's a weak base, it accepts a proton. And so we can do other things to ammonia, and we can put different groups where the hydrogens are. We can put a propyl group and two methyl groups, or we can have a benzene ring put on one of these hydrogens were on NH3, or we can have a methyl and an ethyl and leave the hydrogen on. So all of these molecules, which are called amines, are derivatives of ammonia, NH3. So not too different. We know that nitrogen makes 3 bonds as opposed to carbon's 4 bonds. And we have this lone pair that likes to be by itself. However, we'll learn this can be protonated. And moving right along, just like alcohols, we can reference how many carbons are attached to a nitrogen. And if we only have one carbon to a nitrogen, we call it a primary amine. If we have two carbons attached, as you see here, two methyls, we call it a secondary. And if we have three methyl groups attached, we call it a tertiary. So a primary amine, secondary amine, and a tertiary amine. Not unexpected, as we remember how alcohols were defined. Here are some examples. In ammonia, we cannot call ammonia a primary amine or a secondary. It's just ammonia. It's a weak base. There's the structure of it. And it's more pyramidal type structure. But then we go to our first primary amine, and we call this methylamine. So we have a methyl group replacing one of these hydrogens. Then we can have two methyl groups replacing two hydrogens on ammonia, and we get a secondary amine, and we call that dimethylamine. And then we can have a tertiary amine by replacing all hydrogens with methyl groups, and then we get trimethylamine. So that makes sense. And what further can we don't have to just add methyl groups. Let's add an ethyl group. So we would get ethylamine here, and we could add, of course, we already seen this dimethylamine, and we could add a couple methyl groups and an ethyl group, and then we would use the alphabet that E comes before M. So we ignore the di, the tri, or what have you, and this becomes ethyl dimethylamine. And that's pretty simple, maybe. And we can look at these as alkylamines, meaning that they're alkylated, which means carbon and hydrogen attached. So, how do we write the names of these compounds? Well, we look at A, we see it looks like an ethyl, or not, excuse me, not an ethyl, but a propyl group is attached. So that looks like a propyl group, 3 carbons. Here we have a methyl, and an ethyl group. So let's see, how are we going to name these? And we can, the first one, very simple, it's just propyl goes in front of the parent, which is amine because amine takes priority. So it's a propylamine, it's a primary amine. B, we should be able to see that that's a tertiary amine. It's got 3 different carbons attached around it. And so we have ethyl and 2 methyl groups. So ethyl dimethylamine, ethyl goes in front of methyl. We ignore the di, the tri, etc. And when we name these, as we've been doing previously. What if we get an aromatic ring involved here? Well, remember what we learned previously, that a benzene ring attached to an ammonia group is called aniline. Okay, but if we put a bromine at the 4 position right across from the amine, we would want to call that 4-bromoaniline. And these can be used in dyes and other industry processes, maybe drug synthesis, all sorts of cool stuff. We can also take this nitrogen, and we don't have to just leave hydrogens on there. We can add a methyl group onto that amine. And if we do that, it would become what? N-methyl aniline. Okay, so N stands for the nitrogen, a methyl group on there. We have to kind of know by default that there has to be since it's aniline, there has to be the nitrogen there that's attached to the benzene ring, and we have the methyl group, and the hydrogen by default would be there. And so that's a secondary amine. And this one here, very simple, 1, 2, 3, 4. It's going to be 4-bromoaniline. And we just use that root aniline, which is used for many dyes, not unlike indigo that we just saw, which is a little more complicated of a molecule. But this can be aniline can be used for dyeing silks and cotton and all sorts of things. So let's see if we can write a common name for A. Well, we have ethyl here, and a methyl here. So we kind of know that it's going to be diethyl methylamine. We look at this, we see aniline, don't we? So we say, oh, that's going to be aniline. So this is, and then we see an ethyl group. So this looks like it's going to be N-ethyl aniline. So let's see what we get. So yes, diethyl methylamine. We have a tertiary amine, and here in ethyl aniline, we have a secondary amine, just as we suspected. Okay, so what do we have here? Propylamine, ethyl propylamine, and diethyl methylamine. And by the name, we should kind of be able to draw this propylamine, ethyl propylamine. So we know we have an ethyl group on one side, a propyl group on the other side, and that's it. And then we have a diethyl methylamine. So we know we have 2 ethyl groups, and then we have a methyl group. So that's going to be a tertiary amine. Not too surprising. So primary and secondary amines with fewer than 6 carbons typically can be soluble in water. If we start adding more carbons after that, we may have troubles. Um, Tertiary amines, the hydrogens are no longer there to hydrogen bond with other tertiary or other amines in there, because tertiary amines do not have any hydrogen, so they can only form hydrogen bonds with the lone pair of electrons or the nitrogen. So with water, with respect to, remember, hydrogen bonding, that's not going to go away. Very essential. Hopefully you've mastered hydrogen bonding to some degree and feel confident. Um, yes, hydrogen bonding. Primary amines, NH2, can readily form more hydrogen bonds than a secondary amine. And tertiary amines have no hydrogens on the nitrogens, so it does not form its own hydrogen bonds, but it can bond with water and the nitrogen atom. And of course, ammonium can certainly bond with water. It's a weak base. It's going to accept a proton as bases do. So awesome. So a little bit like alcohols. Alcohols might be a little bit more soluble in many cases, but they're quite similar. They can interact with water. So when does an amine become insoluble in water? When does it become insoluble? Well, when you have these really long chain carbons, one, two, three, four, five, six, well, you got three here and one, or two here and three and one here. So this is maybe a little bit soluble, but not so much. So it still does, it's getting longer with more carbons. If we added two more carbons to here, it would be insoluble. So we have to be aware of that. And the solubility properties is still the rules about when you get six carbons or more, it's difficult for something to be soluble. This one here has six, seven, has nine carbons. Okay, so which of the following compounds are soluble in water? Well, this here is a primary amine with three carbons. That's certainly soluble. You have two hydrogens that can bond with water, and the nitrogen definitely going to be soluble. We look at B, we see one, two, three carbons. Uh, we're missing a hydrogen because now the nitrogen's kind of locked in between here, kind of like an ester would be. And there's a hydrogen, so we can definitely be, this would definitely be soluble in water too. C, we just have all carbons. There's nothing to hydrogen bond at all with water. So butane would probably separate out from water. Although it is kind of a small molecule, it still will be fairly insoluble in water. So you can look over those answers. Um, just a reminder, what does ammonia do? When it interacts with water as a weak base, it can take a proton from water, not from all the water molecules, but a few of them, and become NH4 plus, which is a charged species, kind of like a complex ion, which means all these, just for reference, all of these components here are soluble. Then we have hydroxide ion, which a hydrogen was lost on the water, and so that's basic as well. And remember now, if I asked you, left side is reactants, right side is product. Which one is probably in greater excess? All things with no tampering with anything, not adding any salts. I'm not adding any ammonium chloride to make a buffer. Of course, this side is much more concentrated. There's much more ammonium in water than there is ammonium ion and hydroxide ion. There's very little of this. And you might say, wait a second, Mr. Pryor, hydroxide ion is really a strong base. That's not going to last very long. You're right. But you have to remember, we're in a solution this is very dilute. This is very dilute. Um, okay, so yeah, this is going to reverse, but um, uh, this ammonium ion NH4 plus and this hydroxide ion hardly exist in the solution relative to ammonium and H2O. So let's take a look at methylamine reacting with water. It does the same thing that we would expect, except it has a methyl group and it's protonated and it gets a positive charge too, and it makes a hydroxide ion once the water loses its proton. And so again, it's the same situation. Which side has the most concentration? Which side has the highest concentration? Of course, it's going to be the left side, the reactant side. This is also a weak base, and this methyl ammonium ion and hydroxide ion are in low concentrations. The methylamine and water are, of course, in higher concentrations. Why? Because both of these are weak bases. And amine salts. So what we have is when we have a unprotonated amine, we often get a smell, not sometimes horrible, sometimes not so bad. Amines in fishes react with, of course, lemon juice, and that neutralizes the odor because you end up putting a positive charge on the amino group. Um, kind of like what we just saw, but we're using acid instead of water, and water is acting like an acid. But let's use a strong acid. So if we have methylamine and we use hydrochloric acid, okay, this is not an equilibrium. This is a very strong acid, HCl, and it completely protonates methyl ammonium chloride, and you get a salt in a methyl ammonium chloride being fully protonated is positively charged, floating around in solution, and it can kind of pair up with chloride, all of this dissolved in water, of course. There's no equilibrium here. All of the reactant becomes this product. As long as there's enough HCl available to protonate the methylamine, all of that will become methyl ammonium chloride. The same thing with the dimethylamine. Strong acid is going to completely protonate that and make it dimethyl ammonium chloride. Okay, so amines can be converted to their ammonium salts and used as a drug. And these salts, of course, can be solids if they're they can be dehydrated, and you can have solids of these, and you can dissolve them in water and, of course, body fluids, which is necessary. And a couple of them that we might want to look at that are medications is ephedrine hydrochloride, that has a positive charge on it. And that positive charge helps it float around in the aqueous milieu of the cell and the bloodstream. We have diphenylhydramine hydrochloride. Diphenylhydramine HCl is the same as Benadryl. And so ammonium salts are used as active ingredients in medications. They're pretty safe. Of course, you have to be careful. Ephedrine, bronchial dilator, and asthma, and decongestion, of course, Sudafed. Diphenylhydramine found in Benadryl. It's used for relief of itching and pain and skin irritations and rashes, and also can help with sleep. But again, you have to be careful with that. Well, this is kind of an illicit drug, and they're just explaining it's the same thing. We're dealing with amines that get protonated, which become ammonium salts. Uh, comes from a plant, right? From a cocoa plant, cocoa leaves. So this gets acidified when it gets extracted through an aqueous solution. So it comes out of an organic solution from the leaves, and it's protonated, and one can reproduce. It can reduce this, or excuse me, can remove the proton, can neutralize this positive charge and get rid of the positive charge, and you come up with this drug that is illegal, that can get people in deep trouble. So we see below here, it just talks about how it's treated with strong base to yield the free amine um, as necessary. This can be used for all sorts of different types of drugs. This trick works quite well. An extraction tool to bring it into water by acidifying it, it takes it out of the oil side of things and brings it into water. And this is a very common thing that you will do if you take organic chemistry, except with not that drug. Okay, so looking at this, we see nicotine. Um, Nicotine, again, we're looking at a amine, but this one is a tertiary amine, and it's an alkaloid, and which means it has base properties. It has base-like properties. When you see alkaloid, that means it's going to have carbons and nitrogens, and it's going to have base tendencies. And it is active in plants, and it's used in anesthesics and antidepressants and stimulants, and it is also very habit forming. And although it does seem to help with the levels of adrenaline in blood, heart rate, and blood pressure may increase, and it can be very addictive, which is bad because we don't want to be addicted to anything. Although we are addicted to water, right? We do need water. But looking at caffeine, okay, wow, lots of nitrogen in caffeine, another addictive alkaloid, meaning it has some base properties and lots of carbons, and has some carbonyls and a couple double bonds in this. Quite unique and very popular drug of choice in chocolates and soft drinks, and can stimulate the nervous system and promote alertness and insomnia. Might be a good thing to sometimes even prevent accidents, maybe that people are woke, that they have their caffeine and they're ready to go. And so we get into more of these drugs that some are illicit and some have practical uses. Morphine relieves pain, so can codeine. And Unfortunately, heroin is a byproduct of some of this, which is a very damaging drug and very addictive and one of the worst because of the side effects. So here's a poppy plant, very unique, as you can see, but you see the nitrogens that are within morphine and codeine. They're not very different molecule at all, is it? You see a methylation here where an ester is formed with this benzyl ring, and this is all these rings are fused together in codeine. And in morphine, you see that the methyl group is off, and it's just an alcohol. So quite similar, isn't it? But a little bit different properties. And so now they want us to write these structures, methylpropylamine and 2-chloroaniline. So with methylpropylamine, we know that we must have a nitrogen with a propyl attached on one side, a methyl group on the other, and a hydrogen. With the 2-chloroaniline, we know we're going to have the benzene ring with NH uh, attached to it, and then we're NH2 attached to it, and then at the position 2 of the ring, we're going to have a chlorine. So let's see if we can draw that, and there we go. Methylpropylamine, just as we would suspect, a methyl group on one side, a propyl group on the other, and hydrogen, of course. So it is a secondary amine. Um, 2-chloroaniline, of course, is a primary amine, and just as you would suspect. And you could put the propyl group on either side or the methyl group on either side, and you would be fine. Even with this chlorine, you could put the chlorine over here. Okay, because if you this is a pancake, if we had another molecule that had the chlorine over here, we could flip it and it would be the same molecule because unlike cyclohexane, just one last follow-up point. This is a very different molecule than a benzene ring. Okay, this is a very different molecule. There's no double bonds here, right? There's no three double bonds in this. This is just all sigma bonds, single covalent bonds, and it's not flat. This is not flat. What I'm pointing at here is not flat. This is flat like a pancake. In fact, cyclohexene has all these conformations and chairs and interesting geometry, and it looks like this from the side. It is not flat at all. This is flat. So be careful. Cyclohexane is not benzene. They are two different molecules. I will see you guys. Thanks for showing up. Take care.